Okay.
Fabulous.
That sounds great. Okay. Hi, everyone. Welcome to Communities Workshop with Noelle. Thank you so much, Noelle, for coming here today to present with us. So a little bit more about Q-munity. Q-munity is a student-run organization that is dedicated to spreading more awareness and educating everyone on what quantum computing is really about. And today we have the one and only Noelle Ibrahim here to talk a bit more about quantum computing. So I'll pass it on to Noelle.
Hello, welcome everybody, and thank you for joining my talk. I'm Noelle Ibrahim, Industry Consultant for Banking and Financial Markets at IBM in the Quantum Center of Competence, and I'm also an IBM Quantum Ambassador. And so today we'll be giving a bit of an introduction to quantum computing, starting with Quantum 101. So there are many problems in science and society and within business that are difficult to address with classical computers. The first example here we'll talk about is improved nitrogen fixation processes for creating ammonia-based fertilizer, new catalysts to make CO2 conversion into hydrocarbons more efficient and selective, better financial models to improve stability, predictability, and growth of world economies, new classes of antibiotics to counter the emergence of multi-drug-resistant bacterial strains, for example. These are just a few diverse examples of the types of problems that classical computers struggle to deal with, and which we hope quantum computers in the future will be able to deal with, and for which there is theoretical foundation and reason to believe that that will be the case. So problems we can't address adequately today abound, such as the examples we just gave. However, there are several problems that we can address today. There are also problems that can be addressed with quantum computers that cannot be addressed with classical computers. For example, factoring. So a classical computer can actually do quite well with multiplying two large numbers together, but factoring one large number is something that is very difficult for a classical computer to do. Now, quantum computers are not as efficient as classical computers in terms of multiplying two numbers together, but they are much, much, much more efficient, exponentially more efficient at factoring a large number. There are also problems in simulation of natural phenomena that is based on the laws of quantum mechanics that quantum computers are much more adept at solving than classical computers. There are other problems such as optimization, Monte Carlo simulation, and AI and machine learning, which are subjects of current research and for which there are some theoretical proofs, for example, in the Monte Carlo simulation, that quantum computers can accomplish certain tasks with fewer iterations per algorithm execution. And as we just briefly touched on, there are three major areas in which it's thought that quantum computing will contribute to solving computational challenges. The first we touched on already was simulating quantum systems. So it makes sense that if a system is quantum in nature, it's much easier to compute properties of that system with a computer that actually obeys the laws of quantum mechanics itself. And we'll see later on that quantum entanglement is very difficult for a classical computer to simulate and requires an exorbitant number of classical bits. And so obviously the quantum entanglement in natural systems is much easier to simulate with a quantum computer. The center bucket here is artificial intelligence. So different model training, better model training, pattern recognition, for example, fraud detection is one of the areas where we think quantum computing will contribute, because quantum algorithms can detect more complex patterns within data than classical computers can actually detect, and different types of patterns, often involving entanglement. Finally, optimization and Monte Carlo, we also touched on. So some of these areas in which quantum computers might contribute through better optimization and Monte Carlo algorithms are portfolio optimization, risk analysis, loans and credit scoring, and Monte Carlo-like applications. So for decades, we've been describing the world in terms of zeros and ones. I'm sure you are all familiar with the classical bit, which takes on the value of either 0 or 1. But the fact is, the future isn't just zeros and ones. The future lies with qubits, and qubits, like classical bits, can take on values of 0 and 1, but they can also take on values that represent linear combinations of 0 and 1. So as you can see here on the left, we've described the qubit with a spherical diagram here. At the top pole, one sees 0, at the bottom pole, one sees 1. But the quantum state can actually act like a vector that points to different areas on the surface of this sphere. And the probability that one measures a 0 or a 1 is given by the distance between the quantum state and the pole 0 or 1. Now, when I say probability, that means that the superposition state of 0 and 1 is actually not, it's something that the quantum computer can operate on, but in a logical and predictable fashion. But when it's measured, the laws of quantum mechanics are obeyed, and an outcome of 0 or 1 is recorded with only a given probability. Now, the laws of quantum mechanics, including entanglement, superposition, and interference, allow the quantum computer to operate on zeros and ones in parallel, and then perform operations using quantum circuits to get to the correct answer to a given calculation. Now, on the right here, we see a quantum circuit. And what one sees here, this column here, is that the state of a quantum bit starts off at state 0. So it starts off at this pole here, but then it is rotated by these pink gates. So it gets rotated such that the state is, the state is somewhere here along this curve. These blue gates perform entanglement. And then, as you can see, there are layers of rotation and entanglement here, and finally a measurement state. So this quantum circuit can manipulate the superposition state until the point of measurement, when the answer collapses to either 0 or 1. And using the properties of interference, entanglement, and superposition, one can design algorithms such that the best answer becomes apparent more quickly than it would with a classical computer. So quantum bits are fundamentally different than classical bits and obey the laws of quantum mechanics. Now, here's a little bit of information about entanglement, and just to illustrate how difficult it is for classical systems to actually simulate quantum systems. So the amount of information that is contained in 2 qubits requires 512 bits, assuming 64-bit precision, in order to describe it. 3 qubits requires 1024 classical bits. And once you get up to 160 qubits, you need more than all the atoms on planet Earth to simulate those 160 qubits and their quantum mechanical properties, including entanglement. And as you see, 280 qubits would require more than all the atoms in the universe. So we can do calculations fundamentally more quickly with quantum computers than is possible with classical computers for certain types of calculations. Now, we are in the early stages of a new technology, and as we see, we're in the later stages of a technology when it comes to classical computing. And we've all heard of Moore's law, which shows that there's an exponential growth in the power of classical circuits and the number of transistors that can be deployed to a circuit over time. However, we're slowly reaching the physical limits of what we can do with transistors and making them smaller and smaller, and therefore making more and more powerful integrated classical circuits. However, what we see on the right here is a new version of Moore's law that shows that the power of quantum circuits of quantum computers is exponentially growing. And in fact, recently, we've seen this departure from the exponential curve to an even greater accelerated pace of development. On the left here, one sees that this axis is labeled quantum volume. Quantum volume is a measure of the power of a quantum computer. So quantum volume measures not only how many qubits there are in a quantum computer, but also how many sequential operations can take place on that computer. So that's why it's called a volume, essentially. So quantum computers accumulate errors every time there's a new gate applied. And so only so many gates can be applied before the errors accumulate and make it too much for the processor to compute the calculation properly. Now, on devices that we expect to be available in the midterm, we expect these to be noisy intermediate scale quantum devices where errors will accumulate within the quantum volume. And that's why we use quantum volume to describe the power of the processors. However, in the long term, error corrected quantum computers will become available, and they will require about 1,000 physical qubits for every logical qubit. However, as you can see, progress is happening quite rapidly, and especially with the Montreal system here, we're getting ahead of the curve now with a quantum volume of 128 on IBM systems. And that brings us to the IBM roadmap. So as we see here, IBM has published a roadmap for their plans to scale quantum technology. And where we are today is we're at the Hummingbird machine with 65 qubits. This year, we're expecting the release of the 127 qubit Eagle machine, going on to the 433 qubit Osprey machine in 2022. And then finally, the 1,121 qubit Condor machine in 2023. And as we see here at the bottom, each of these scale ups is dependent on a key advancement. And then finally, once we reach that level of having 1,000 qubits, we reach an inflection point where a logical qubit can be created from physical qubits. And that will bring us to error-corrected computers of 1 million qubits and beyond sometime in the future. Now, the idea of the error-corrected qubit is that multiple qubits work together to create a type of redundancy that depends on group theoretical properties of certain logical qubit states. So instead of having a state 0 or a state 1, we have a logical state 0 and a logical state 1 that have certain group theoretical properties that allow for operations to be performed without accumulating errors. And that's thought to require at least 1,000 physical qubits for each logical qubit. So we're really expecting 2023 to be an inflection point, not only because this is the getting first to the scale where we could create a logical qubit, but also because in terms of the depth of the circuits that are required and the number of qubits that are required for more midterm level algorithms to be successful, we expect that inflection point to come in 2023. So key takeaways. To take advantage of IBM Quantum's increasingly powerful hardware, we are announcing a detailed development roadmap through 2025 as well. And the key takeaways of the development roadmap are the Qiskit runtime to run quantum applications 100 times faster on the IBM cloud. And this has been made available now to members of the IBM Quantum Network. Dynamic circuits will be introduced to bring real-time classical computing to quantum circuits, improving accuracy and reducing required resources. So there are many algorithms that are designed to communicate back and forth between quantum and classical systems, and having the classical system right next to the quantum system can reduce latency. So we're also looking at quantum workflows, so Qiskit application modules to lay the foundation for quantum model services and frictionless development. So what do we mean by frictionless development? That essentially means that the tools that will be required to use quantum computers will be made as close as possible to the tools that developers are already accustomed to using. So for example, Qiskit is written in Python. And for those familiar with Python, it's very easy to learn Qiskit. One can also go to the open source Qiskit textbook. So from a computational language point of view, there shouldn't be hurdles there. And as we see here, the development roadmap first starts with kernel developers who develop circuits and are more involved with like pulse level types of building pulse level types of applications. And then we have algorithm developers. So these are people who actually develop new algorithms to take advantage of quantum hardware. So such as academic researchers, for example, and other applications researchers in industry. And then at 2023, we expect to have quantum model services such that the previously developed algorithms can now be used to develop models with business applications in mind. Of course, the algorithm developers do develop algorithms with respect to business applications, but these quantum model services will be a little bit more applied than even these model algorithm developers are working on right now. So my area is finance, and some of the areas in which we see useful applications for quantum computing in the business world are in finance. And for example, portfolios that may adapt to market changes more quickly than portfolios that are optimized using classical methods is an example. So portfolios with higher order moments, for example, are very difficult to calculate with classical optimizers. Even the best in class optimizers, such as CPLEX, for example, have certain types of objective functions that they find challenging to calculate. So if you find such an objective function, and one example is this portfolio optimization with higher order moments. That is, if one looks at the distribution of stock price returns, one looks at not only the mean and standard deviation, but also the skewness and the kurtosis. That can be very difficult to calculate, but with a quantum computer, one can use optimization methods such as QAOA or VQE, or in the long term, one can use Grover's type optimization, Grover adaptive search, to find more optimal solutions more quickly than classical computers, given that you need a certain level of accuracy. Quantum machine learning algorithms can also detect new and different types of patterns than classical machine learning algorithms. So finding new approaches to cope with financial crimes is one of the use case areas within finance as well. So there's now with 24/7 access to banks through multiple digital channels, there's more opportunity for financial crime, and financial crime is actually escalating, and the patterns are always evolving. So being able to reduce false positives, for example, is one of the key priorities in industry. A false positive occurs when, for example, a transaction is labeled as a fraud but isn't actually a fraud. And if one wants to be conservative and catch more frauds with your model, you're also going to have more false positives if your detection algorithm is not perfect. So if you can get better detection algorithms that can better separate fraud from non-fraud, or for example, money laundering from non-money laundering transactions, one can actually reduce the number of customers that are wrongfully turned away. And that's one of the business priorities that we're looking at with quantum support vector machines, for example, and other quantum machine learning algorithms. Finally, liquidity processes that keep pace with Basel regulations and other types of regulatory applications, such as fundamental review of the trading book, are areas that of interest, especially when parallelization of Monte Carlo simulations is expensive during the day. Many regulatory requirements call upon the estimation of a concept called value at risk, which is essentially looking at how much money a bank might lose if an extreme event occurred. And that is usually calculated using a Monte Carlo simulation, and these can be quite intensive. Parallelization can reduce the time it takes to do these types of calculations, but at some cost. And so quantum Monte Carlo simulations can actually reduce the number of trials needed to come to an answer. So the number of trials needed for the quantum computer is quadratically less than the number of trials needed for the classical computer. However, the classical computers do catch up when they use parallelization. However, in other words, well, Monte Carlo simulation can be massively parallelized, and I guess I won't go into the details of that here. But the point is that when parallelization is expensive, it can be worthwhile to find alternative methods for calculating concepts such as value at risk, which is the amount of money that a bank can lose in a given extreme circumstance. This is another quantum machine learning application. So thinking about personalized customer experiences and refining client targeting by better understanding their behaviors and connecting those behaviors to outcomes using quantum machine learning algorithms that are capable of detecting more complex patterns than classical algorithms are able to detect. So this is another area in which we think the quantum machine learning algorithms will be applicable. And quantum machine learning algorithms are complementary to classical machine learning algorithms, detecting different types of patterns and possibly being able to work in concert with classical algorithms to produce better prediction outcomes. So of course, before these quantum algorithms can be truly deployed, we do need more advances in the hardware, such as detailed in the IBM hardware roadmap. But there is some evidence using simulators and small deployments on current devices to show that these algorithms do work and have potential. So most of these algorithms fit into the three buckets we discussed earlier: optimization, simulation, and machine learning. And here's just a few examples of optimization, simulation, and machine learning in the financial services industry. So portfolio management and transaction and security settlement fit under optimization. Value at risk, credit risk, and pricing of derivatives fit under simulation. And under machine learning, we have credit scoring, fraud, anti-money laundering as examples. So the IBM Quantum Network is an open source, and also it's both inclusive and exclusive. So there are inclusive elements that are open source, such as the Qiskit textbook and the Qiskit open source code repository that anyone can use to develop quantum algorithms. And then if one is a member of the IBM Quantum Network, you also get access to premium hardware and also can conduct research, for example, with IBM researchers. But here's an example of how the community is growing and working together. So IBM Quantum published a paper on amplitude estimation. Keio University caught on to this paper and published with the banks Mizuho and MFG. JP Morgan Chase applied the method to options pricing and published, and then open source code was contributed to Qiskit for all to use. So as we can see, there's a very vibrant, active community out there of individuals learning from each other. And this is one of the key differences between the way technology is developing today as compared to the way technology developed in the early days of classical computing. In the early days of classical computing, access was very much restricted, and only a few people could actually develop classical computers when you think back to the 1940s and even the 1960s. But today, with open source and the internet and the cloud-based services, there are many more synergies and much more growth of ideas through community that is causing a rapid acceleration in progress. So this is just an example of one of the papers that has been published recently on applications in finance. So this gets a bit technical, but you can also find these papers available online if you'd like to read them yourselves. But this just goes over quantum amplitude estimation. Here you see this a quantum circuit here on the bottom left. In the middle, we see portfolio optimization, where if you're familiar with the efficient frontier, one can see that the quantum algorithm called VQE, variational quantum eigensolver, actually does find the same portfolios on the efficient frontier as the classical algorithm, even though it's a very new and nascent technology. And then here on the bottom right is a circuit that is a quantum machine learning, implements a quantum machine learning algorithm. So here we see an illustration of the application of quantum amplitude estimation to value at risk. And the most interesting thing on this page is to look at the acceleration of the training here for the quantum algorithm as compared to the classical algorithm. Now, if we look at this graph here on the bottom right, we see that although the classical algorithm begins with a lower error than the quantum algorithm, the quantum algorithm quickly catches up and is expected to surpass the classical algorithm in terms of lowering the error on its estimate more quickly with the number of iterations. So, for example, the number of iterations in classical Monte Carlo simply means the number of trials that the number of samples that one draws for a probability distribution that represents your problem. And in the quantum algorithm, the number of trials means something slightly different. It's basically a rotation in a complex Hilbert space. But because there are fewer of those needed, after a certain period of time, it's faster to use the quantum methodology. So sometimes that period of time is very long and not practical, but in other times, especially when parallelization is not possible, it may become useful. Here's another example. This is transaction settlement. So this is an optimization problem where one tries to close as many transactions as possible. So one optimizes over the number of closed transactions here, and the quantum circuit is on the bottom right. And what is shown here is a number of rotations and entanglement interactions followed by a measurement. And this essentially creates a trial wave function, which is a superposition over bit strings, where the bit strings represent which transactions are closed and which transactions are not closed. And a classical algorithm then for each of the bit strings evaluates the value of the cost function that describes the problem, and then iterates upon this circuit, changing the parameters of the circuit until the trial wave function that is generated is focused on the bit string that represents the solution to the optimization problem. So here's an example of customer segmentation. So this just shows you a little bit about the types of decision boundaries that are detectable in feature space with quantum algorithms. So what we see here illustrated on the top right is a decision boundary with a large margin that was determined by a quantum machine learning algorithm for a certain type of data that was generated to require such a decision boundary. And as you can see, it's quite complicated. And this type of decision boundary would be very difficult to obtain with a classical algorithm. So in this case, this is a QSVM, quantum support vector machine, that uses a quantum generated kernel. And what's interesting about this is that the quantum generated kernel can actually be used in a classical support vector machine, and then the decision boundary can be found within that quantum Hilbert space. by the classical machine learning algorithm, as long as the kernel itself is computed by a quantum algorithm. And now this kernel is usually the inner product between it, like one might be, for example, you might be familiar with radial basis function kernels from support vector machines, which essentially look at the distance between different data points. The idea is that if a data point of class 1 is close to another data point, then that other data point is likely also class 1. And there's a decision boundary that can be drawn in that space. Now, instead of measuring the distance using, say, a Euclidean norm or using a radial basis function type of approach, one actually uses the distance between two quantum states, or the inner product between two quantum states, where the data is encoded in the quantum state. And then that forms the basis for the quantum kernel, which can then be analyzed by the classical support vector machine apparatus. So this is a little bit more about quantum machine learning. So here we see a paper called A Rigorous and Robust Quantum Speedup in Supervised Machine Learning. And essentially, if we look at figure B here on the right, this is what the classical computer sees. It sees essentially what looks like a random distribution of class 1, which is red, and class 2, which is our blue points, and it cannot draw this separating boundary between the two. Now, the quantum support, yes, it is a quantum support vector machine using quantum kernel estimation, actually sees this figure here, figure A. So it is able to use Shor's algorithm, a kernel building algorithm that uses Shor's algorithm as a subroutine in order to solve the discrete log problem. And that allows it to actually see the separation between the red and the blue classes. And then once that discrete log problem has been solved, a separation can be found in that more complex feature space. And as we can see here on the far right, figure C, the large margin is still preserved. So essentially, the wave function that is formed is a function of the data point itself, and it forms a superposition of wave functions, which are very much separated by this large margin right here. So although it doesn't concentrate around a single wave function, it's guaranteed to have a large separation between the wave functions that class 1 map to versus the wave functions that class 2 map to. And this speed up is exponential because it's actually based on this discrete log problem, which is related to Shor's algorithm. And of course, the factoring problem. So the IBM Quantum Network is all about collaborative community of discovery, where we hope to reach out to groups like yourselves to get involvement from the community, educate and train individuals. Like I said, there's the open source Qiskit textbook anyone can use to learn quantum computing with Qiskit. We accelerate research and we develop applications. So what is it that builds a quantum workforce or a quantum community? So open access, open source, and education are some of the foundations upon which we hope to accelerate development of both quantum hardware and quantum algorithms. So the frictionless developer environment that we're aiming for aims to create tools, as I said earlier, that classical developers are already using, such that classical developers can develop using quantum algorithms in a frictionless way, i.e. there'd be little to learn in terms of the language and in terms of building the applications. Well, in the future, there might be less to learn in terms of building the applications, but if one wants to develop models if one wants to develop algorithms, it's really important to understand how the quantum architecture works. But the aim is to have a frictionless developer environment that is as easy to use as possible for those who already have development skills. So the same tools, the same languages, and the same code can be used to program a quantum computer as to program a classical computer. That's the principle. This is the open source textbook that I keep mentioning, and I would urge you all who are interested to go and check it out because it's got really great information and also allows you to get that hands-on experience. So it has some exercises, and you can go to the IBM Quantum experience, create an account there, and just start programming and start learning quantum computing. Finally, we're enabling research with 400 plus papers and counting. Those are, of course, publicly available. Like if you go to the archive, for example, you can find many of them. And in the Qiskit documentation, you'll often find references to papers that you should be able to find on the archive. This brings me to the end of my talk. And I guess that leaves us with about 15 minutes left for questions, if anyone has any.
Thank you so much, Noelle. We do have some questions in the chat. Well, the first question we have is, are there any resources you recommend us to get started with? I think that was before you recommended that online textbook, but are there any other resources you think that might be good for us, especially?
Yeah, I think papers on the archive are really great. If you have the background to read like the scientific papers, I think that can be helpful. There's also the Qiskit documentation. There are also videos on how to use Qiskit by an IBM employee named Abraham Asfaw, ASFAW. You may look for those on YouTube. Those are really useful. There are also a variety of other open source resources, I think, available now from some other companies. Like I think Xanadu has Penny Lane. There are other resources out there, but IBM's the best, so use IBM. No, but yeah, I think we have the most resources available, like the textbook, for example.
Yeah, for sure. I see another question about the quantum volume and reducing latency. So is speed like the biggest advantage when it comes to quantum computing? Are there any other advantages that we might foresee in the future compared to classical computers?
So I'm not sure I quite understood the question. So there were two parts. There was something about quantum volume, and then there was something about advantages compared to classical computing.
Yeah, so the question was about like the quantum volume, and you discussed about how it kind of reduces latency. So the first question is, is speed the biggest advantage when it comes to quantum computers, and are there any advantages you notice that might come up in the future with quantum computers?
Well, I think speed in terms of the number of iterations, for example, that are required to execute algorithms is probably one of the biggest, like the biggest advantage, if not one of the biggest advantages. But to be clear, with what we know today about tomorrow's architecture, which obviously there could be many developments between now and the time when a fully fault-tolerant, error-corrected computer is available. But with what we know today, the gate times are actually slower for quantum computers than for classical computers. However, so many more gates are required, like so many more steps are required for the classical computer that it actually makes the classical computer slower. So just to understand what speed means here, speed is like to make it a dramatic analogy, I would say if you compare, say, driving in downtown Toronto compared to walking in downtown Toronto, you would rather walk most of the time because you can go directly to where you want to go and there's not going to be any traffic. If you drive, it's actually going to take longer, even though a car is faster than walking. The car has to go in circles and circles and circles before it finds a place to park. So it actually takes longer. So that's kind of like the difference between quantum speed up and classical speedy gate times, if that makes sense. But in addition to the speed up, there's also the fact that quantum may find different types of relationships and different types of like optima when one is computing an optimal value. So essentially, like there may be some improvements in performance metrics, such as like false positive rates or finding a lower minima of an objective function. That's something that we are investigating.
Yeah, that's really cool. I like the comparison with walking in the car. That makes a lot of sense now that you've explained it. Okay, so the next question is, how does a logical qubit differ from a physical qubit? And what are the limitations or new opportunities available with a logical qubit?
So with the logical qubit, essentially what happens is that rather than errors accumulating, if the error rate is below a certain threshold, the errors actually will start to diminish with every step in the algorithm. And that's because of like very complex, like group theoretical types of design of the logical qubits and the gates surrounding the logical qubits. So one of the main differences between a logical qubit and a physical qubit is that a physical qubit actually takes on the value of 0 or 1. Like, so the 1 state is actually like the first excited state, for example, of your quantum system, and 0 is the ground state of that quantum system. However, a logical qubit is actually like a entangled and superposition state of a number of qubits together, so that one can be represented by like a superposition of bit strings like 11011 plus 00111011. I'm just making these up, right? But there are actual definitions, and I don't have them memorized, but there's a definition of what a logical 1 is, and it's a superposition of different bit strings. So that's the main difference, and they're chosen because they have certain group theoretical properties. So it all gets pretty complicated, but the advantage is that one can actually do deeper circuits because errors don't accumulate. Like with noisy intermediate scale quantum, every time you execute, especially like certain types of gates, errors accumulate in your calculation, and after a while too many errors accumulate such that you can't get the outcome that you want. However, with the fault tolerant computer, those errors actually don't accumulate, so one can actually do calculations with millions of steps. So certain types of algorithms like Shor's algorithm and Grover's algorithm are only executable in a fault tolerant quantum computer because they require so many steps.
So would you say that is it possible to have logical qubits without needing any more physical qubits? Is there a point where you can just use logical qubits, or do we always have to have a physical qubit?
I think you have to have some kind of physical qubit that like system of qubits that are going to have these quantum mechanical properties. So logical qubits are generally made up of physical qubits, just so that they have these certain properties that will allow them to do the quantum calculations. I hope that makes sense.
Yes, that makes sense.
Okay, I hope that answered your question.
Yeah, of course. So one more question in the chat is, so stocks are, this is the question regarding like the finance. So stocks are quite hard to predict. So you said in the talk that quantum computing can help kind of predict like these stocks. So how do we really measure the accuracy when it comes to with quantum computing and stocks, and what factors do we need to consider that we can input in the quantum computer?
So in portfolio optimization, what one is trying to do is actually maximize the amount of return that one gets for the amount of risk that one takes. So for example, if you think of like a Gaussian distribution, if the Gaussian distribution is very wide, that's a lot of risk. If is very highly peaked, like for example, if the average value is high, then that kind of represents a lot of return. But if it's wide, you don't know how much that return is going to be. And there's something called Markowitz portfolio theory, which essentially talks about the efficient frontier, which helps you essentially properly diversify a portfolio so that you get the maximum amount of return for the amount of risk taken. So if you have, for example, a lot of correlated assets, then that's unwise because the amount of return that you'll get for the amount of risk taken is much lesser than if you have a diversified portfolio with uncorrelated stocks, because the fact that they're uncorrelated actually reduces the width of the Gaussian as you add them together, for example. This is just an intuitive way of understanding it. So you're not really trying to predict the stock's outcome in particular, but you're trying to say how much return do I expect to get for the amount of risk that I have. And what one actually inputs to the quantum computer, or any computer for that matter, is something called the correlation or covariance matrix between the stocks. So looking at the covariance of the stocks with respect to each other, and then the standard deviation of the returns of each of the stocks along the diagonal. And one can also compute higher order terms. So everyone knows that stock returns are not actually Gaussian. Like you've probably all heard of like fat tails or black swans or that type of thing. So you can include higher order terms in there like skewness and kurtosis, and try to optimize your risk using, for example, measures like Sharpe ratio. So what you'd be essentially measuring is getting a better Sharpe ratio from the portfolio that you choose. And if you can take into account these higher order moments, you should be able to choose a portfolio that better accounts for the risks that you're actually taking, and therefore get a better Sharpe ratio. So Sharpe ratio is just the returns divided by the risk. So that's like mu, your average, divided by sigma, your standard deviation. So
okay, thank you so much.
That was a lot of info, I know.
Yeah, it's all right. We can watch the recording back over and like slowly understand everything. Thank you for technology. We can record all this down.
Yes.
So we have another question in the chat. So how are IBM computers different from other quantum computers that already exist in the market?
So IBM quantum computers, like the hardware is essentially a transmon qubit. So that is basically, it uses a Josephson junction, and it actually forms a quantum state through that Josephson junction, and there's a current that goes through it, and it is sort of like a harmonic oscillator. I don't know if there are any people with physics backgrounds in the audience, but harmonic oscillators manifest certain types of quantum states with discrete energy levels. So you have like energy level 0, energy level 1, energy level 2, energy level 3, etc. But the way the transmon qubit works is it's actually an anharmonic oscillator, because the problem with a harmonic oscillator would be that you'd be able to excite the atom from, or not the atom, but the particle from the ground state to the excited state, and then to a second state, which you don't want. You just want the states 0 and 1. So this anharmonic term actually separates the second state from the first two, such that the probability of exciting it to that state is very little. And it's manipulated essentially with microwave pulses, and that induces like Rabi flopping and that type of thing, if anyone learned about that in physics. But the microwave pulses essentially can excite it from the ground state to the first excited state, or cause it to fall down through essentially like a spontaneous emission type of process from the, or like, yeah, not spontaneous emission, sorry, like a stimulated emission process from the excited state to the ground state. So that's the IBM hardware. Now you might have heard of Honeywell, for example, or IonQ. They use ion trap quantum qubits. So basically they have atoms or ions that are trapped by a lattice of lasers. And then they use the actual energy levels of the atoms as the 0 and 1 states. And now the difference between the ion trap and the superconducting qubits is that the ion trap qubits tend to have longer coherence times, but they also have slower gate times than the superconducting qubit. And then finally, another type of computer that is commonly known as the D-wave system, for example, which is a quantum annealer. Now, that's not a universal gate-based computer. It actually is mostly meant for optimization problems. So it differs from the ion trap and the superconducting qubit in terms of the fact that it can't do any like universal quantum computation, and it uses a phenomenon called quantum annealing, which basically takes a starting, like it's using like sort of an icing model, i.e. like a bunch of magnets with spins that interact with each other. And then it superimposes magnetic fields on that to manipulate the energy levels of those spins and they are connected to one another. And then one starts with a, I guess, an initial Hamiltonian, and then slowly, so an initial energy function or Hamiltonian, and then slowly morphs that into the Hamiltonian that represents the problem of interest. And since one starts in the ground state of the Hamiltonian, that is the initial Hamiltonian, if you actually evolve that system slowly enough, you stay in the ground state of the problem Hamiltonian. So that's how you find, for example, like the minimum of an objective function in optimization with that type of computer. But that's a very different process than what occurs with a gate-based computer.
Thank you so much.
Okay.
Really great. Thank you so much.
You're welcome.
So one final thing that people are wondering is if there's any way we can like reach you to contact you for any other questions regarding the talk. We will be uploading it to our YouTube channel, so some people may be wondering how they can ask you questions from there.
Sure. Well, I think you probably have my email address, or you can find me on LinkedIn. So I'm on LinkedIn under Noelle Ibrahim, and I think Sarah and I are connected. Or you could email me, noelleibrahim@ibm.com. I might be pretty busy, so it might take a while to respond to like a lot of questions if that happens. But yeah, probably email or LinkedIn is a great way to reach me.
Yeah, for sure. I'll share your LinkedIn and your email with the video on YouTube, so people can contact you. And thank you so much. That was an amazing talk. I loved it, and I loved all the questions that people asked, and I loved all the answers.
Yes, great questions. Thank you, everyone.
Have a nice day, guys. Thank you so much, Noelle. Have a nice day.
Bye-bye. You too.
You too.
Bye.